Today we'll be going over how to create this particle simulation animation, which uses a geometry node setup and the merge by distance node to create both collisions and attraction between particles. So let's get started by going through the geometry node setup. It consists of three major parts, starting with the initialization of the particles, going on to the main simulation loop, which we'll explore all the innards of, and then moving on to the render preparation at the end of the network. So to begin, let's go through the particle initialization nodes. Now, the way that we want to initialize this setup is with a 3D grid of particles bounded by a sphere. So if I pull up a viewer node, we can see the initial 3D grid of particles that we are creating using this 3D grid node group. This group works by taking an integer resolution as input, creating both a grid and a line with the amount of points on each corresponding to that resolution, then instantiating the grid along each point of the line so that you get a cube of 3D grids that are then realized and converted to points in order to create the output 3D grid of points. So to bring in another viewer node into this network, what I can do is show you this initial grid here, as well as the curved line, which is initialized with a simple curved line node, which is then resampled to get the correct resolution. So that you can see there. Then I transform that curve, just translating it down half a unit in order to bring it to the center of the scene, or to the center of the space that I'm currently working in. Then I use an instance on points node to instantiate that grid across each point of that line. And now all the vertices that we have in this output mesh are the points that we want for our eventual grid. You can realize the instances, which just makes these instances real so that we can actually convert the mesh to points and then pipe that into our group output. So once we have our grid, we want to delete all of the points that are outside of a certain spherical bounding region. So that's done with this delete geometry node, which deletes a selection of points whose lengths are greater than 0.5 in this case, which is just the radius of the sphere that we're keeping points inside of. So if I make that smaller, the sphere gets smaller, larger, it gets larger, and that's our bounded sphere. And now we can move on to the main portion of this node setup, which is the simulation loop. So briefly, to go over the major steps, we will capture the start position of all the particles. We will update the position of each particle by its velocity. We will add forces to each particle. We will evaluate constraints, which in this case are collision constraints as well as a boundary constraint. And then we will update the velocity of each particle with an attribute. Then we will update lazily the velocity, which is used for the coloring in the final render in the shader nodes. Then we will update the max speed, which is also used within the shader nodes. And then we will continue the loop. So starting from the beginning, we will capture the start position. This is a simple group where you're just capturing the position attribute of all of the particles. Then you update the position by its velocity attribute. And what we do here is we add in a scaling node to add a little bit of velocity dissipation over time, so that as the simulation progresses, the particles lose a little bit of velocity each step and eventually come to a stop. Then we add forces. There are two types of forces that are present in this simulation. One is a noise force, which just pushes the particles around by a noise texture. So sampled by each point in space, the particle will get pushed in a certain randomish direction based off of a certain scale. And then a particle force, which is used to create an attraction force between the particles within a certain distance of each other. Each of these force node groups outputs a vector, which is then used to change the position of each particle slightly. So the way the noise force works is that you sample a noise texture based off of a position which is offset and rotated in order to create variation in the noise force over the course of the animation. Then you subtract 0.5 from each of the noise texture channels in order to make the noise force randomly push in a range from -1 to 1 in each channel, and then you scale the force by a low value, in this case 0.02, in order to make sure that the noise force is not creating too much of a change of each particle position each frame. So the offset and the rotation of the sampling position for the noise texture are done purely to create variation in the noise force over time, which is just something that you would do to make the animation look nicer. In this case, we're using the scene time node, using the frame output, and then dividing by 64 in order to create a small variation in the angle of this position vector as rotated along the z-axis. So sort of along this axis, rotated like this over time. And then this offset node here, the addition of a z channeled vector to the position is also just done to get a sampling position for the noise texture that I liked for the animation. So you don't need this one at all, and you can change these values however you want to get an animation that you think looks good. Then we set the position of each particle using the noise force as an offset, and we move on to the particle force node. This node group functions by taking in the particle geometry as an input, merging that geometry by distance to find the midpoint between sets of particles within a certain distance of each other. It then finds the proximity of the original geometry's position to the merged geometry's position to get the actual position of the midpoint in relation to each particle in the simulation. It subtracts the position of the position of the midpoint from the position of the particle to get a vector in the direction from the midpoint to the particle. It scales that vector by a certain amount. In this case, we're scaling by a negative value because we want this particle force to be attractive rather than repulsive. And then you pipe that into the group output, which becomes the particle force that then, just like with the noise force node, you piped into a set position node in order to change the position of each particle in the simulation just a bit in the direction of the particle force. Moving on to the evaluation of constraints. In this part of the simulation network, what we're doing is we're finding two types of constraints. The first is a collision constraint between particles, which is done in a very similar way to what we covered in the particle force node, and also a force which constrains each particle to the bounds of a sphere. We have three constraints node groups chained together here, which each have 9 iterations of a collision step node group, which create 27 collision steps which are needed to help converge on a good solution for non-colliding particles that are constrained within the sphere over the course of a single step within the simulation loop. So what that means is we have all these little particles in our simulation, and they all have a radius. Let's say some of them are colliding. Now, between these two colliding particles, what we want to do is find a vector which points in a direction which separates the colliding particles. So the idea in the nodes that we're using within this simulation is that if you've got a certain number of particles within a certain distance of each other, they will be colliding. And what we do is we find the midpoint between all those particles, and then for each particle we find a vector which points away from that midpoint, and then we move those particles in that direction. Let me delete this stuff. So what we have then is this midpoint with these particles that have been updated in that direction. Now, we have 9 steps per constraints node group, and we have 3 of those, so we have 27 total steps. Because to make the simulation stable, you want to make these corrective vectors very small, and you want to iterate on them a bunch of times. Because let's say in this situation you have this midpoint and these particles, but then I also have a particle right here, so that when you correct the position of this particle by that vector, then in this case now those two particles are colliding. So you want to have multiple steps between steps in the simulation or per frame, so that then you'll find another midpoint between these two particles, create correction vectors, and then you'll get a state in which all these particles are not colliding with any other particle. And so as you can imagine, these sorts of interactions with more particles can happen many, many times within a time step. And so the more collision iterations and corrective iterations you have, the closer to a correct solution you'll get for each time step. The distance parameter for each of these constraints node groups is the same, because we always want the size of the space between particles in which corrective vectors are calculated to be uniform, because particle sizes are uniform within the simulation. But the scales for each constraints network are a little bit different. And the reason for that is because I found just having a number of collision iteration constraints at a larger scale than a slightly smaller one and a smaller one after that produced a good result. So diving into the constraints network, you'll see that we have these 9 chained collision step node networks which inherit the distance and scale parameters from the outer constraints node group. For each collision step, we undergo a process very similar to this particle force node group, in which we merge by the distance of the parameter that is inherited from this outer network. So if you've got the particles, let's say they're within that distance of each other, then you merge that distance and you get this single particle right in the center, or this single position in the center of these three particles. Then we get the proximity of the new geometry to the old geometry. And so for each of these particles, the position output is the position of this new particle. So then what we do is we subtract the position of this new particle from the position of each of the old ones to get a vector between the new particle and the old one, pointing from the new particle to the old ones. And then that is going to be our corrective vector after we apply some small transformations to it. Those transformations are a normalization vector to make the length of each of these vectors to be 1. And we just do that so then we can then scale the correction vector by the scale parameter, which again is inherited from this outer node group. So we can control the distance that each particle moves in each correction step. And so that movement is enacted here in this set position node. And so you just pipe in that scaled corrective vector into the offset input. And then we calculate the corrective vector for the sphere bounds, which is separate from the corrective vector for the particle collisions. So the way that this sphere bounds network works is that the bounds that we're dealing with in this simulation are to keep the particles within a sphere whose origin is 0, 0, 0, and whose radius is this parameter. So in this case, a radius of 3. So what we do is we take the position of the particle in question, we get its length, because that will be the distance of the particle from 0, 0, 0, which is also the center of the bounding sphere. Then if that length is greater than the radius of the sphere, which we input here, then we're going to want to apply a position offset. So we do that by setting the position of a selection of particles that fall outside of the radius of the sphere. And so for each one of those, the corrective vector is just a vector that resizes the location vector of the particle so that its length is the radius of the sphere. So what that means is that we've got this bounding sphere. In 2D it's a circle, and you've got particles, some are inside, let's say this one is outside. So this is the 0, 0, 0 position, and the length of this vector is the distance between 0, 0, 0, or sorry, the length of the particle's position vector is the distance between 0, 0, 0 and the position of this particle. So if that is greater than the radius of the sphere, or the circle in this case, then what we're going to do is we're going to set the position of this particle to this point on the sphere. And the way that that's done is we just normalize the vector, the position vector of this particle to create a length of 1, and then we scale that normalized vector by the radius of the sphere or of the circle, and that creates the vector that is on the bounds of the sphere. So then we simply set the particle position to that new position, and that is the spherical boundary constraint. And so we repeat those collision steps 27 times, and then we are done with the evaluation constraints portion of our simulation network. Next, we update the velocity attribute of each particle. So what we're doing in this simulation is each frame we are changing the position of each particle by both the velocity, the forces, and the collision constraints. And then we're updating the velocity based off of the difference between the particle's position at the beginning of the simulation and the particle's position at the end of the simulation. So if we go back to the beginning of our simulation loop, that's why we have this capture attribute node, which is capturing the position of the particle so that we have the position of the particle at the beginning of the simulation loop. Then we go through and we do our velocity update, we do the force update, the evaluation of constraints, and then we're looking at the difference between the new particle position and the particle position at the beginning of the simulation. So we subtract the particle position now from the particle position at the beginning of the simulation, which gives us this vector. And then we're storing that as the velocity of that particle. And now we're getting into the parts of the simulation loop which are only present in order to get the desired shading for our particles within rendering. So we have this update lazy velocity. So what's happening here is when we're rendering our simulation, each particle has a color that corresponds to the speed that it's moving, which is based off of the length of the velocity. And so I found in rendering the simulation when I was creating this that if you just use the velocity of each particle, it can be a bit noisy because sometimes the velocity will change quite quickly because of the collision constraints. So instead I wanted to make it sort of change more slowly over time. And so what you do there is I have a separate lazy velocity attribute, and what I do is I take that and I just interpolate it towards the velocity attribute by just a little bit over time. And I use the mixed color node for this. It's just an easy way of doing that. So really I'm just mixing the value of the lazy velocity towards the velocity by 0.01 each simulation step. And then you just store that in the lazy velocity attribute, which we'll use later within the shader nodes. Another area of this simulation loop that we're using for rendering is updating the max speed attribute. And so what this attribute is used for is again for the coloring of the particles. And what it does is it finds the maximum length or the maximum speed of the lazy velocity attribute between all the particles. So the fastest particle will have the speed of this max value. And then in the shader network, we use that to scale the factor of the color so that you make sure to have colors that fall between a range of 0 and 1 so that you don't get a bunch of red particles or a bunch of blue particles. You sort of get an even range between the whole spectrum of colors that we're working with. And so with that, we have finished our simulation loop, and we can then prepare our particles for rendering. And we do that by instantiating an icosphere onto each particle of the simulation. So we create an icosphere, we set it to shade smooth, we instantiate it on the points of the simulation, and then we realize instances. Now, the realize instances node is super important. If I take that out, you'll see that the colors disappear. That's because if we want to use the attributes of our simulation that we created in the simulation loop, as in the max speed, the velocity, and the lazy velocity, then we need to add in this realize instances node, or else that data won't carry over into the render. So after all of that, we can actually press play and watch our simulation move. And so you'll see the noise forces sort of pushing these particles in random directions, and you'll see that the collision constraints both keep them within the sphere bounds as well as keep them from intersecting with each other. And if we keep the simulation playing, we might be able to see some instances in which the particles bunch up at the edge of the sphere boundary. And if there's a lot of them, you'll actually end up seeing the collision constraints not work out. But because of the number of iterations that we're doing and the number of particles that we're working with here, the entire simulation seems to work quite well. What we can also do is we can look at what the simulation would look like without some of the constraints. So if we go down into the collision step node and we remove the actual particle collisions and just do the sphere bounds collision, then if we restart our simulation, you'll see it moves a lot quicker. So about twice as fast, maybe 3 times as fast, but the simulation is way less interesting because all the particles just kind of clump together. So you can see how important that particle collision step is, even though it slows down the simulation by about half. So not so bad. You're still running at 5 frames per second. Additionally, we can look at what happens if we remove some of the other forces. Like, let's remove the particle force, which is the this is the particle force, which is the attractive force between particles, which creates these kind of clumps that we'll see over the course of the simulation. And you'll just see that the particles are a little bit looser. They don't cohere together. You've got all these hanging particles, whereas if they're attracted to each other, then that wouldn't happen. So if I reconnect that node, you can see that the distance I have for the attractive force is at 1, which is a whole lot larger. Well, it's 10 times as large as the distance for the repulsive force, which governs the particle collision constraints. And so if we set that value a lot higher, let's set it to 4, how about, then really all these particles are getting attracted to each other. And so you'll just get this one massive ball of undulating particles, which is kind of cool. Looks nice. but I like the distance set to 1, or let's try 0.5 or 0.4. Let's do 0.5. And you can see that you'll still get clumps, but much smaller clumps. So you can kind of tune these values and create a simulation that you find interesting, but that's what you're working with. So I'm going to set that back to 1, and we'll move on to the shader nodes. So going over the shader nodes for this simulation, let's run the simulation just a bit. Turn on rendering. Now you'll see that we've got a couple of things going on here. First, we're bringing in the two attributes we discussed before, which is the lazy velocity attribute and the max speed attribute. So really from the lazy velocity, we're just getting the speed, and that's done by just getting the length of the velocity, or the lazy velocity attribute. And then we're dividing that speed, so the lazy velocity of each particle, by the max speed, which is the speed of the fastest moving particle at any point in the simulation. After that, we get into artistic territory. So I'm adding a power node with an exponent of 2, and that's just to change the distribution of the colors a little bit. So I just like to have a little bit more on the blue end of the range than would be present without this power node. Then I have this color ramp node with these 5 colors set to RGB. I could set them to HSV actually. Wouldn't change much. But these just go from blue to red. And then we pipe the output of the color ramp node into this hue saturation value node, just to bring the value down a little bit, because if we have it set to 1, it's too bright. So then what I do is I have the output of this hue saturation and value node going into the base color. I have it going into the subsurface color as well. That's just a holdover from experimenting with using a little bit of subsurface within the shader, but I'm actually not using that, so you can take that out. And then that's the shader. So relatively simple. It just maps the speed of each particle onto a color. And that's pretty much it. And that is how you create this particle simulation animation with collisions and attraction in Blender 3.5 Alpha's simulation branch. I hope you enjoyed this tutorial. I hope you learned something. I hope you had fun. And if you want to dig into the blend file and look at the rendering setup and the lighting setup and any of the other details, it will be available for free on Gumroad. I'll put the link in description. Thanks again for watching, and have a good morning, evening, day, whatever it is. Thanks a lot. Goodbye.